Today's video is going to focus on modeling. So we are going to model physical situations, most of the time physics-based, but sometimes chemistry-based, using differential equations. So let's just jump right in. Anytime that you're talking about a model, you need to identify any variables that are changing in the system, and you're also going to need to identify a set of reasonable assumptions. For physical situations, usually time is involved. And so oftentimes the solution will be in terms of time, and it will describe the system in the past, the present, and the future. So let's take a look at a few different examples. A free-falling body, like a ball. So let's say here is our ground. We have some ball that is shot up in the air, and it comes back down to the ground. So that is modeling what is going on. Well, we're going to have to take a look at some assumptions. So our main assumption is that we are accelerating at a constant rate. And we're going to have some initial conditions. As we've seen before, we're going to have the initial height of the ball, and we're also going to have the initial velocity of the ball. Okay, so acceleration is a second derivative. So we would have the second derivative of position with respect to time. We know that we're moving downward, and it's at a constant rate. Okay, so this is our second derivative with respect to position, not with respect to, second derivative of position, s being position, with respect to time. After the ball goes up, it starts falling down, so we have downward acceleration at a constant rate. Now, because this is second order, we're going to need two different conditions. We know that the position at time 0 is s naught, and we know that the velocity at time 0 is v naught. That can also be written as s prime of 0 equals v naught. Either one of those will work. Now, because we have s at 0 and v at 0, this is an initial value problem, not a boundary value problem. Same value of x. Okay, so let's look at the next one. Next one, we're going to be taking a look at mass on a spring. So let's say we have our ceiling here, and we have some spring. Attached to that spring, we have some object that we're going to say has mass m, and that object is pulling us down. So right here, we have the equilibrium position. And we want to look at how far that mass is being pulled down. So that is going to be described as x of t. So in terms of time t, this mass is being pulled downward. Okay, so this is in a picture what's going on. So what we're going to say is we are going to define that downward position as being positive. So we're going to say the downward position is positive. Okay, this is where some of you who are in physics might recognize some of this. First thing that we're going to have to talk about or introduce is Hooke's law, which is F equals negative kx. Then we're also going to have to take a look at Newton's second law, which is F equals ma. Okay, so if we set those equal, we get negative kx is equal to ma. So we have to think of what are we trying to get to? We are trying to get to a differential equation. Differential equation. So looking at what we have so far, we have to figure out which of these is a derivative. Well, a, of course, is a derivative. So this becomes m. Acceleration is the second derivative of position, in our case x with respect to t, is equal to negative kx. So there we go. This is our differential equation. Now, there's a few different ways that this might be written. Sometimes we're going to want to get this set equal to 0, so it might be written as m second derivative of x with respect to t plus kx equals 0. Sometimes you're going to want to get a lead coefficient of 1. So if we divide by m, we're going to get the second derivative of x with respect to t. Now if we divide by m, we're going to have k over m. That's just a constant, so we're going to write that as omega squared. It's the same as k over m. So all three of these are acceptable. All three of those are acceptable. And you're probably asking yourself, why are we using omega squared here for these constants? It has to do with solving this equation. So because this is second order, having something squared here is going to make it easier to solve. That doesn't matter right now for you. What you need to know is that any of these are acceptable. Okay, so a lot of this should be familiar from physics. One thing that's going to be different is the units that we use. So in physics, you use these units for each of these variables. For us in differential equations, we're going to use some different units. You don't need this now, but you're going to need it later. So for F, instead of newtons, we use pounds. Okay, this is the one that you probably haven't heard of. For mass, instead of kilograms, we are going to use what is called a slug. So you're probably asking yourself, what the heck is a slug? So let's take a look at an example. We know that mg in physics gives us the weight of an object. So if we want mass and our g, we're going to use 32 feet per second squared. And our object is 8 pounds. That gives you the mass then is 8 over 32, or 1/4 of a slug. And that slug is in pounds per second squared over feet. Okay, for distance, instead of meters, we're going to use feet, which means that for acceleration then, we're going to use feet per second squared, not meters per second squared, which is 32. Again, you don't need these now, you're going to need them in the future. Okay, so now that we've done a quick break with units, let's just go through more examples. Example 3 is a review that you probably saw in Calculus 3, maybe not, but it has to do with Newton's law of cooling. So Newton's law of cooling says the rate at which a body cools is proportional to the difference in temperature between the body and the surrounding medium. Okay, in this case, it's going to be a really good idea to have a figure. So let's say this is our cooling body, and it is in some surrounding medium. So we're proportional to the difference in temperature between the body. So we're going to need something to represent the temperature of the body. So I'm going to do T of M, and that is going to be the temperature of the surrounding body. Okay, we want to know the temperature of that cooling body, so that's going to be T of T. So that's going to give us the temperature of the body at a specific time. Okay, so the rate at which the body cools, rate, that's a derivative. So that is the derivative of the temperature of the body at time t is proportional to the difference between the temperature of the body and the surrounding medium. And so that should look familiar. You've seen that before. We don't have enough information in this case to write any initial conditions. Okay, another one that is not going to be a shock to you is population growth. So here's what we know. The more people there are, the more there will be. So this is our assumption. So our assumption is the more people that there are, the more that there will be. So what does that mean in terms of differential equations? That means that the rate at which P, the population changes, is proportional to the current population time t. Okay, so the rate at which P changes, the rate at which the population changes, that's our derivative with respect to time, is proportional to the current population. That's it. That's the entire differential equation. Okay, so those are the ones that you've likely seen before and that are pretty quick. On the last page, there's actually two more that are certainly more difficult and going to have a little bit more work. So let's end this video with the last two examples. Okay, so we are going to consider a tank with water where A of B represents the area of the base and A of 0 represents the opening at the bottom of the tank from which water is draining. Suppose that the speed or velocity of the water leaving is given by V. What we want to do is find a differential equation that models the height of the water in the tank. Okay, the very first thing that we're going to have to do is draw a picture so we actually understand what's going on. I didn't say this, but it's a cylindrical tank. Or the problem doesn't say this, it should, but we have a cylindrical tank. Okay, so A of B is the area of that entire base. And then at the bottom of that base, we have a hole where water is draining out of. So the size of that hole is A sub 0. What we are looking to do is model the height of the water in the tank at a certain time t. Okay, so looking at our goal, we need to model the height of the water in the tank. Okay, so thinking about what we're going to need. Height of the water in the tank, so we're going to need a rate of change. And we need to keep in mind that not only is the height changing, but the volume is also changing. Okay, so where does this go? First step, the rate at which the volume is changing. The volume is decreasing, and it's related to the area of the hole and the velocity at which the water is leaving. So this is the rate of change of the volume in the tank. Again, negative because the volume is decreasing, and it's going to be the size of the hole multiplied by how fast the water is leaving. So that's the first thing that we need. I should have said this earlier. Ultimately, what we're looking for, if we need the height of the water, we're looking for dH dt. That's what we have to find. So we're going to need to get something in terms of dH dt. Okay, so second thing that we need is let's talk about how to find the volume of this tank. Well, the volume of this tank would be the area of the base of the tank multiplied by the height. And volume and height change over time. So we see a little clue above, we have dV dt, and so maybe we decide that we're going to take the derivative with respect to time. Keeping in mind, volume is changing, height is changing, but A of B is a constant. So when we take the derivative, we're going to get dV dt is equal to A of B times dH dt. dH dt is what we're looking for. So where does this lead us? If we solve for dH dt, we're going to get dV dt times 1 over A of B. dV dt, though, we don't want a derivative, a second derivative, so let's use the expression we have above. So we get dH dt is equal to negative A naught over AB times root 2GH. So that is our differential equation. Okay, that one was definitely a lot tougher than the ones we've previously done, so I want to do one more example so that we can go through this process together. And it's this example 6. A large mixing tank initially holds 300 gallons of water in which 50 pounds of salt has been dissolved. Pure water is pumped in at a rate of 3 gallons per minute, and the resulting solution is pumped out at the same rate. Find the differential equation for the amount of salt in the tank, A of t, at time t. So again, it's probably a good idea just to start with a picture. So we have this tank, and this tank has 300 gallons of water, and it has 50 pounds of salt. Pure water is pumped in. Okay, so we're pumping in water, pumping in pure water at a rate of 3 gallons per minute. We're mixing up the solution, and then we are pumping out at 3 gallons per minute. We are looking for the amount of salt in the tank at time t, which means that we are going to need dA dt. Okay, so if we want to know dA dt, we want to know the amount or the rate at which the amount of salt is changing. Well, we need to take what's coming in and subtract what's coming out. In terms of what's coming in, the salt that's coming in, there is no salt coming in, right? It's pure water that's going in. So we need to take a look instead at what is going out. Okay, we're looking for a concentration. So we know that this is leaving at 3 gallons per minute. Our concentration of the salt is going to be in pounds per gallon, which then we're going to see gives us a rate that's in pounds per minute. So we need to figure out at time t, how do we figure out how much salt is in the tank? Well, it tells us that the amount of salt in the tank is A. So the concentration at any time, there's going to be A pounds of salt over that 300 gallons. That's our concentration. And that's because we start with 300 gallons. There's 3 coming in, but 3 leaving. So we have a constant 300. That 300 doesn't change, but the amount of salt does. So when we simplify this, we're going to get A over 100, or A of T over 100, either one of those. So our dA dt then, the rate coming in is 0. We're subtracting A over 100. So what that gives us is that dA dt is negative A over 100. Might be written as dA dt add A over 100 equals 0. So both of those are the same. You could also, like I said above, express A as A of t. So it might be expressed as dA dt plus A of t over 100 equals 0. And that's just showing that A is a function of time, which should make sense. As time is changing, the concentration is changing. And in this case, we do have the initial condition, right? So this is order 1. We only need one initial condition. So the concentration at time 0 is that 50 pounds that we started out with. Okay, there are more examples in your book if you want to look through them. This one is going to be hard, but hopefully the background that you have in physics will help. If you have any questions, please make sure you bring them to class. Until next time.